Okay, so welcome. It's my pleasure to introduce today's speaker, who's Alfons Van Blaaderen. Most people, I don't remember when I met them, and particularly when I met them a long time ago, because Alfons is almost as old as me. But I do remember when I met him. I was working at Exxon Corporate Research, and he showed up with his postdoctoral advisor, Pierre Wiltius, who I knew. And Pierre's a pretty tall guy, and so I don't like tall people because I'm used to being the tallest person in the room, and it's unusual for me to have someone taller come in, and it creeps me out. But I was prepared for it with Wiltius, so Pierre. But he walked in with his postdoc, who I expected to be some short little guy, and his postdoc's even taller than Pierre. I still remember the discussion. He talked about using confocal microscopy to do templated crystal growth. That was a great experiment, by the way. That was really, it's one of the classic experiments of colloidal science, showing how you can template the growth of colloidal crystals. Beautifully studied with confocal microscopy, which was pretty new at that time. Matter of fact, I know Alfons published papers on confocal even before that one, and so the earliest confocal papers I'm aware of in colloidal science are Alfons. Maybe somebody else did it earlier, but I don't know. At any rate, he went back to Holland and became a professor at the same place that he got his PhD at Utrecht with a guy named Rye, and who's a very famous colleague, and has continued to do really pretty work over the years. A lot of work on photonic crystals, and some really nice work with one of our former postdocs, Marion Lewison, on oppositely charged colloids. So lots and lots of really creative ideas have come out of this guy's head. And I know a little bit about today's. I think you'll be pleased with the talk. He has some really pretty results to show. So welcome.
The mouse right there. Could you grab the mouse right there? Mute it and hit got it. Okay, just me and I'll hit it.
All the contents are gone. Yes. Thanks a lot for this very nice introduction, and also for this opportunity to talk to you about a self-assembly route that we're following now already for about 8 years. I'm also very grateful for the staff of the Soft Matter Center here at NYU for giving me the opportunity to spend my second sabbatical here. First sabbatical was 16 years ago. I think after Willem Kegel, I was the second one as a guest here of the Soft Matter Center. And I still distinctly remember, and it's too bad Paul Taken isn't here right now, but my 3-year-old twin daughters, one of them likes chocolate a lot. And all of a sudden she was watching through a window and said, "It's all chocolate." And she was referring to this barrel that I just checked is still in Paul Taken's office, filled with M&Ms. And because she was allowed to take a handful out of it, she now still remembers being 19-year-old that she got all this chocolate from this person. So that was also, by the way, about self-assembly of anisotropic particles, but we'll get to that here in a minute as well. And as mentioned, there are other connections to soft matter scientists also over the very many years. So let me see why this is not responding. Is it? Because perhaps I should click on this. Yes. And now we go to the second slide, I hope. Yes. Something that I don't, because of time, want to forget is I'm going to show you quite a bit of results, because this is a very knowledgeable audience in soft matter. This work on assembling particles in slowly drying droplets. because that's the approach that we use to do self-assembly on multiple length scales. Because in that way you can get a self-assembled structure that, and I'll actually go back to the previous slide. If you look at the scale bar, that is still on the colloidal size range. So you have now a crystal of, in this case, binary nanocrystals. Here's iron oxide and gold, and there's two kinds of semiconductors that you can self-assemble yet another time, because 300 nanometers forms still beautiful photonic crystals. So you've manipulated the structure, for instance, to be interesting. Semiconductor can be emitting photons, and then you can do another self-assembly step. You can actually, and we've recently done that, also self-assemble these supraparticles in another supraparticle, and well, you get the idea. So Davang is the one who most recently got his PhD, and all the theses and all our papers are downloadable from this website. We always very much collaborate with computer simulators and theorists, in this case, particularly with Marjolein Dijkstra. Tunishta Dasgupta did the simulation work, of which I will not show all the movies because I saw there is some lags with large movies, but I'll show some frames of those. And Ernest van der Wey and Michiel Hermers did a lot on the quantitative real space analysis. We also worked, I'll show you a little bit of the work together with the group of Daniel van Makenberg, and these groups are all in the Brownian Institute for Nanomaterials Science, which in Utrecht houses groups both with a chemistry background and a physics background. And a lot of the projects I will touch upon today were also done in collaboration with Sarah Bals, who has a very good group on electron microscopy, and specifically electron microscopy tomography. And we also collaborate, especially learning from them, from the masters, the self-assembly of nanoparticles by the group of Chris Murray, who is in Philadelphia. Okay, I want to couple also to the beautiful talk of last week. So it was already mentioned, and actually I have even a slide to show that you know, you can put it in the ground for about 50 million years, you take it out, and lo and behold, there's still colors. Perhaps a little bit less bright, but almost as bright as this beetle when it died 50 million years ago. So that is indeed an important point. Structural colors are not chemical in nature, so they don't, the molecules don't degrade. Certainly in time with organic dyes that would happen. But this connection with Kramers-Kronig and the real part and the imaginary part of refractive index was also noticed by us already 20 years ago, when we made photonic particles with the metalloelectric shell. So these are gold particles, actually gold shell, only 20 nanometers thick, a few hundred nanometer diameters. And they also show extremely brilliant colors. So these very brilliant colors, there is an example here of the jewel beetle to be bought for $12, and there is no connection, but in the evolution shop right across the street there in Broadway, also uses partially absorption to get this brilliancy. And it's also fairly omnidirectional, although the Morpho Butterfly in their careers office is even more omnidirectional. So these are clearly not omnidirectional. The colors change quite drastically just with this change of orientation. But what we want to go to is not to keep these colors 15 million years the same, but what now if you could change the colors dynamically and actually quite fast. So that's a little movie from the internet, but that inspires me still quite a lot. And you probably see by the name already what we're going to look at. But to me, this is quite surprising still, and it's still not completely understood, by the way. So that guy is colorblind. It cannot even see its whole body, and still, when you were 10 centimeters away from it, you could hardly distinguish it. And then he used some other some other soft matter to try to disguise himself in an even different way. So it shows, that's why I leave it running. It shows also the same movie, but then backwards in slow motion. And you can really see how fast this changes, but also on how well this is done. So just a few frames back, and you will not recognize anymore that there is an octopus there. The octopus is colorblind. Yes. So how the hell do you do that if you're colorblind? But most of
Why would that be?
well, what the part that I've asked several biologists, and I try to find it out in literature. How can you camouflage yourself so well?
Without knowing what color is right?
Yeah.
Wait, so just a second.
But also, what is the mechanism on how you do that? Because he cannot see himself even, and he can't see colors anyway, but he cannot see part of his body, and still it's perfectly camouflaged. So
What you're saying is surprising that it's
How-
not conscious decision by the author.
no, what is the mechanism? What's the feedback?
By which
Oh,
it matches.
By which it matches, yeah, he cannot see part of the camouflaging part that he
Yeah,
does.
it's not a brain signaling.
As far as I know, biologists don't know.
And
But
it's not only color, it's also texture, and I think that is also
yes,
surprising.
you could see that too, but that's not part of my motivation yet to make. But who knows? But anyway, if you can do that, and we're getting there actually, almost not too far away. Then you can also change of colloids their interactions as well. And if you can change interactions dynamically, you can change self-assembly pathways. And that, I think, is a very important part for future materials development, because not everything that we want is in equilibrium. And to find out pathways in complex self-assembly systems is, I think, very important. And we're working with Marjolein Dijkstra, also using clues from nature and chemistry. Almost all chemical reactions are way far out of equilibrium, so we need clues from chemistry as well. But we try to do reverse engineering. We want to make a collection of potentials, but dynamically changeable potentials, and then design interaction self-assembly pathways. But okay, I will not go there. That's long-term. One of my heroes in physics is Richard Feynman, and you probably all know about this APS meeting in 1959. A lot of nanomaterial scientists say that that was the start of nanomaterial science. It's actually not true. Most of them had forgotten about this talk of him, but it was really well positioned as the start of the nanomaterial science, because he was thinking, what if you could make atom by atom materials? And of course, he was just daydreaming about that. My little add-on to this famous quote is that there is very much room at the bottom if you are able to make materials atom by atom, but there is much more room if you structure materials on multiple length scales with multiple properties. And that is going to be a theme of part of the talk. So some of this manipulating atoms by atoms was already done beautifully by IBM, spelling IBM, of course. But this is some beautiful work from Ingmar Smart in our Brownian Institute from a couple of years ago, where he put carbon oxide on the metal surface in the shape of a Sierpinski ladders, and then measured the quantum mechanical wave function with scanning tunneling microscopy. So this is structuring on the atomic, and if you want, CO is a molecular length scale. Now let's go one tiny little step up and connect it then with self-assembly, the structuring. For that, I show another example from the Dubai Institute, now from the group of Daniel van Akelenberg, also a couple of years ago published. If you have single crystalline semiconductor nanoparticles and let them on an interface self-assemble, where the interface dissolves the ligands, you can actually get it that the single crystals will connect up with the right crystal phase and then make this looks like honeycomb. It's not exactly honeycomb, it's slightly out of the plane. But anyway, almost a lattice that is similar to graphene, where the individual crystal or the crystallinity is just continuous. So if you do electron scattering on or X-ray scattering on this, you see one single crystal. But there are holes, so infinite potential wells for the conduction in the form of all these holes here. So in some sense, it's still very far out of equilibrium, but there is no temperature to anneal out all these holes. So this is already an example, but then in 2D, what is called in the field directed attachment, and I will show you a way of how you can even do this in 3D. So a few slides now, I will be quick on it because these are really old measurements. But our background is indeed in real space analysis, at first with light, with electron microscopy, but with confocal microscopy. But I will also mention that confocal microscopy is now really should be called nanoscopy, a term by Nobel Prize winner in the field, because we can really get to resolutions below 100 nanometers already with light. But if you want to go smaller yet, then electron microscopy is the way to go. And because tomography was already treated last time as well, I will relatively quickly go over that too. So yeah, I did want to mention indeed meeting a lot of soft matter scientists here, because not only you were there, I think Paul Chaikin was there as well at Exxon, and Dave White was associated with the Exxon lab in New Jersey as well. But I connected at Bell Labs during my first few weeks. A faculty staff from Boston came into the labs, and I think you didn't even remember it yourself very well, but you were working on big IDL data stacks and showed me, because I was learning to do image processing, what later became the famous Crocker-Greer code, how to analyze particle coordinates in 2D. And then I set up a little competition with this other guy from Europe, Pierre Wiltjes. He was fitting in 3D to all the intensity distributions. It's a 3D Gaussian. And nowadays, by the way, that's the way to go. So don't take the wrong message from this. But I went the 2D way, kind of Crocker-Greer way, and then do that for each slice, connect that together. And I only had to fit like 5, maybe 10 X, Y, Z data points, and that was done in a millisecond. So it took me about 1,000 times faster to get the same coordinates that Pierre Wiltjes with 3D fitting of his Gaussians did in 3D. But nowadays, we're so many computer cycles further, the way to go is actually the 3D fitting and not the way I did it, much, much faster. So if you have all the positional coordinates, and I don't need to make that point here, you can get a lot of information that for scattering is very difficult. So you can find defects, for instance, out of data, but also I will point out some other examples where real space is quite powerful. Of course, the disadvantage is the averaging over large quantity of data that can be done much more powerful by scattering. But already in this hugely compressed hard sphere solid random closed packed structure, you can see almost 9 peaks in this radial distribution function, which, if you assume that there are pairwise additive potentials, if you measure this radial distribution function as function of volume fraction, you can obtain the particle interactions between the colloids. It was compressed by gravity and actually a centrifuge. So ordinary gravity would get crystals, but 10,000 times gravity you get glasses, and yeah. So fast forward quite only, this is 8 years ago or so, or 7 years ago. And now we can measure in 3D, and I'm showing actually single rods, and it's compressed down. It's a 3D data stacks, but compressed down on one plane, so that it's more easily to show. But I'm showing you this low volume traction system because then the rotations are actually the fastest. We can now, and this is slowed down about 80 times in a glycerol water mix compared to water viscosity, but we can get all the positions of the rods and its orientation very easily in real time. And a full 3D data stack takes only, well, less than 1.5 seconds. And this is already data that is some 7-8 years old. So we can indeed, these are silica rods that were also developed in our group. If you let them sediment and form a sedimentation equilibrium, you find on the top rods that are in a gaseous state. So they are still moving, but you can hardly see that because the data were taken very fast. Actually, looks a lot smoother there, but you can also see we can get all the rod coordinates in even their length distribution from all the individual particles. Here they start to interact somewhat more. It's a colloidal liquid, and very quickly that compresses into a colloidal liquid crystal, which is smectic phase, and then in the bottom you find the crystal. The Van Rooij theorist in our group actually predicted how many of these, in Dutch we have a word for it, it's called a dwarsligger, somebody who goes against the stream, how many dwarsliggers there are, and that's actually quite close to what he predicted in his theory. That was actually huge rods, like 2-micron silica, a few 100 nanometer diameter, so just borderline colloidal. But this is a lot smaller. So the bar is here 50 nanometers. These are gold rods, about 70 nanometers in length, diameter 20 nanometers, but coated with a meso-porous silica layer. That layer is there for a reason. We want to gather analytes in this supraparticle. And then, as you perhaps know, gold rods have a field enhancement at the end of the tips. And by placing them all together, some of these field enhancements overlap. And because it's to the 4th power in the intensity that you boost the signal, you already in such a superparticle get many thousand times more signal than from the same collection of individual rods. And where, of course, we want to go to, but that's not yet, has not yet happened, is that these form smectic phase, because then the gold rods are oriented next to, and their high intensity regions are then overlapping. So then you get a much more increase in signal yet.
So sorry, you mean signal, the signal that you're measuring, or like when people do surface enhance?
This is surface, or we use these structures for surface enhanced Raman scale.
That's right.
Yes.
Yeah, so you just flow in some small molecule.
Yeah, or you can actually throw the superparticle on top of it. If it has some wetness, it will suck it up capillarily even. So that's quite convenient way.
So you probably mentioned this. These are gold nanorods in some sort of droplet. Is that why
They were dried, slowly dried, and self-assembled in an emulsion droplet. I will get back to that, but indeed, that's what we do. We disperse the particles in water and oil, or oil and water, in this case water, and then we dry out the solvent, and then it becomes a permanent structure, of which we can find all the coordinates and the lengths by electron microscopic tomography. We don't use the scattering variant, but just real space projection, and then get the particle coordinates. And that's helped here a lot, of course, because of this low density of silica that's around it that makes the electrons still go through it. If you don't have that, you have to use very expensive focused ion beam slice and view. That was also treated last time, so I will not show that, but that can be done as well. But all the data that I'm showing, and these are the experimental data, so the rods with their lengths and their orientation. And if I show colors, I use RGB values to denote the orientation of the particles. So from the color, you can get their orientation in space. I will go a lot, show a lot of examples of how geometry and self-assembly influence each other mutually. But I do want to point out that these supraparticles are also quite useful for a lot of other applications. I've already, no, the source sensing is the next one. This one is lightning. You probably know that if you make a semiconductor quantum dot, the emission wavelength can be quite narrow, and that's why in some expensive televisions they're already used to produce colors. But nanoparticles themselves are in an industrial scheme hard to use. So simply making 100 or a few hundred nanometer chloroparticles of them is already very useful for industry. However, you then need to do some constructing, because if these quantum dots are closely packed in the superparticle, 1 micron, here the size of the nano colloids is just 10 nanometers, you don't want that an electron hole pair generated is quenched by the one quantum dot next to it. If you would use ordinary quantum dots, that's what immediately would happen. But if you engineer the band gap of the semiconductor, so this is the electron hole pair generating unit, but then have cadmium sulfide, zinc cadmium sulfide, and then zinc sulfide all over it, you make the band gaps every time larger and larger. What it means is that the electron hole pair wavelength does not get out of the nanoparticle. So even if they're touching, and even without their ligand, the quantum efficiency still stays above 50%. So then we can have very nicely luminescing supraparticles. But what now if we make the supraparticles bigger? So these are interesting for televisions, for instance. But if we make them bigger, then optical modes start to appear, whispering gallery modes. It's actually the same physics of a whispering gallery in the Vatican. If you've ever been there, there's like how do you call the shape? Well, a round shape of a corridor, and you're standing here, but then by interference you can quite far away still listen into a conversation. That's why it's called simply by the standing wave pattern, of which there are of course places where it's almost silent, and then there are places where the sound is enhanced, and that was actually apparently used in some of these Vatican rounded corridors. But what happens if you do that with the particles? So of course, trivially, you can mix any color that you want. So you can put them on the color scheme, and if you have green, red, and blue, you can mix them together in the right amount, and then you can have white superparticles where you can select any color that you want. But if you make these particles interfere, so quantum mechanically they're decoupled, but optically they're coupled, and you make them larger, like a few microns, then in the emission spectra, all of a sudden you see all this fine structure, which is showing up these whispering gallery modes. And when one of these whispering gallery modes is enhanced non-linearly, you get lasing, because it's just the same as if you have a die between two mirrors. A non-linear process, light amplification or stimulated emission of radiation, which is lasing, then happens. So then all of a sudden, and now the next graph is not to scale. So this puny peak here is this emission of the quantum dots, is then replaced by this enormous whispering gallery mode, very thin emission of light. This is very interesting, for instance, for sensing, because it's hugely sensitive to what happens on the outside of the supraparticle. And this I already showed, so I'll click this one away. But with a probe die that others also use to test source sensing, we showed in a recent paper. So the details you can read here. It's just as an illustration that several thousand times already for this not yet selectively ordered superparticle, we got enhancement of the source signal. And already the source enhanced rounded scattering of single gold rods is already many thousand times enhanced compared to ordinary round ones. So this is already quite significant enhancement. And if we can make smectic layers, we can get yet another several thousand times more. So now let's go to the gist of the talk. I'll start some older results, and I'm showing actually on purpose also here Dave Pine and Winnie Manahan's paper, because they did similar things but in a different regime. So in their self-assembly, the particles that self-assembled were at the interface only, or almost only. They were smaller clusters. We go to a different limit, where many particles are on the inside. Of course, when the droplet shrinks, also the particles at the interface, in our case, have to pop in, and that costs a lot of KT in energy, but that will happen. But in our case, the self-assembly is taking place inside the droplet. And one other thing that we're doing, which is slightly different than many other groups, we try even with the nanoparticles to have the interactions to be hard sphere-like, which means that we can translate our results for the nanoparticles all the way to optics, and then we get the same results. And I'll show you a few examples of that already. So in our case, most particles are inside droplets. And of course, people were putting already colloids on droplets also way before this work. Weitz called them colloidal zones, but it goes all the way back to Pickering, of course, who even showed that you can use them as surfactants as well. So we try to have hard interactions, and then the self-assembly is scalable. A very short aside, but it's something we're very exciting about. I was always joking in the group, and at some point it became so old that I decided to use it anyway, that microfluidics is you're making colloids one droplet at a time. So how can that be productive? But actually, if you make 5,000 nozzles and use them all at the same time at very high speed, it turns out you can make 100 microgram in about 24 hours of letting the chip run. So that we already knew, and Dave Weitz called his chip the millipede, but the smallest droplets that you could generate were about 15 to 20 microns. So we designed a chip that used geometry to better advantage and get into the colloidal size range. So these are the dimensions. It was designed for droplets of 1 micron, but now, and that's why we call it the nanopede, we can even go to several hundred nanometer sized droplets. So 100 milligram in one day. This is just a zoom in of these 5,000 nozzles that we have over here. And the droplets can be as monodisperse as 3% is the lowest. This is 5%. So they're fully crystallized. And here you see them move in the, so they're the fluorescent quantum dots inside. And now we can do this self-assembly by making the droplets one by one. A workhorse in our self-assembly is this iron cobalt oxide. This is one of the recipes. It is very reproducible, and why we chose this is because it's also a magnetic system, but it's also very interesting for catalysis. Iron and cobalt are important catalysts for the Fischer-Tropsch catalysis. I'm not going to go into any details, but that's why it's an interesting system as well. And you can tune the particle shape. So these are single crystalline particles. The cobalt oxide and the iron oxide grow epitaxially on top of each other. And that's the case, I can show you by tilting these particles just a tiny little bit, and then you'll see that these are core shell actually. And why are some of them completely black and some white is because if the orientation of the crystal is such that it blocks the electrons, then it becomes completely black. But then if you turn it around just 1 degree, then the electrons can go through. But that also shows you that these are indeed even core shell particles as well, because the spacing is just slightly different of the one onto the other. But nevertheless, although they're very nicely spherical, they're single crystals. But we can turn these single crystals from spheres also into cubes and then investigate what does shape do to your self-assembly.
If those single crystals are registered to the underlying crystal, why are some of them rotated by like a degree?
They're not registered.
Okay.
So it's more the other way around. These are randomly positioned in a black position. And if your eye sees some pattern,
Oh, I thought I heard you say that they somehow or other registered to the substrate.
no.
in the background.
The cobalt and the iron are registered to each other. So
Okay.
they have a core shell geometry. So if I would move the whole screen, you would get all crazy because then they would flicker in and out, but you also would see the core shell morphology, which actually is not clear there. But anyway, so many hard, and we try to make them very small because then they're hard sphere-like. But we can make them also dipolar, etc., etc. The big spheres, so this is already millions of particles, do what hard sphere is supposed to do, namely form face-centered cubic crystals. Then some in the audience should say, wouldn't they form randomly stacked? No, these are equilibrium crystals because the nanoparticles have so much time to reorganize that they really go to the equilibrium structure, which larger colloids do not do. This scales with the third power of the radius, so that goes very, very fast if you are so small.
The bare particles are what size here?
10 nanometers. So this is a 50 nanometer scale bar, and well, the resolution is not that great, but you can count the particles. It's less, even including the ligands, is less than 10 nanometers. And you can even, some of you who've looked at these things can even recognize the ABC stacking over here. So this is as expected. For all the smaller superparticles, Barthes came in office, they said they have very complicated twinning structures. I don't know what's going on. How one of these look like is like this. We go through it with this stomogram, and it looks much less ordered. Now that I'm used to looking at it, I actually recognize that this is 5-fold symmetric. That took us quite a few months to recognize that, actually, because you have to turn them in the right orientation, etc., etc. And then we thought, okay, we know that icosahedral ordering happens for metal atoms, and even the Lennard-Jones potential, if you look at clusters, minimizes the energy by arranging themselves in icosahedral symmetry. So we thought it's surely dipolar interactions or anything like that. Turned out to be not the case, because I said, how can we make sure? We scale it up to micron-sized colloids. We do it with light, and we found the same structures. So then we went to Marjolein Dijkstra and said, can you do some computer simulations of self-assembly hard spheres in the sphere? And lo and behold, a few thousand particles also gave icosahedral structures. So then we knew it has to do with optimizing the entropy, because for hard spheres, there is only entropy in the free energy. And it's not so trivial to see or to know. Perhaps some of you do know that if you have one sphere and you try to maximize the kissing number, you have 12 particles around it, then many people would just guess that the closed packed structure of that closest packed structure is part of an HC or an HCP packing. Is actually not true. An icosahedral packing of 12 particles around one particle is the closest packing. How do you define even the packing volume fraction with 13 particles? Well, there's a complex mathematical term for it called convex hull, but you can also just say if you shrink wrap it and you measure what's inside, then that volume fraction icosahedral is a few percent higher than. But it's kind of weird, because if you keep on packing spheres around that icosahedral seed, you keep the 5-fold symmetry. Then who did that actually literally with balls was Mackay in the 50s and the 40s. You get, for instance, the next layer is a truncated icosahedron, which, by the way, I'm sure everybody knows as well as the soccer ball. But if you keep on doing that, you can keep the icosahedral symmetry, but your packing goes to 68 volume percent. So not to 74, but to 68. And that's significantly less. So in infinite size, hard spheres should be close packed. But that infinite size is actually already several, only, or as much as a few 100,000 particles that we never had expected. So several 100,000 particles, the icosahedral structure is the one with the highest entropy. And if you're very good in your platonic solids, then you of course immediately recognize this as a cozy dodecahedron. For the rest of you who don't see that so immediately, that is this one. Well, it's actually funny, I've taken it out, but in the Big Bang Theory, there is actually a quiz going on, and then of course Sheldon recognizes that this is a cozy dodecahedron. But anyway, we had to look it up. But what is very interesting, if you do this self-assembly, where you know for sure that it's not the interactions, you get the same cozy dodecahedron. And if you keep on increasing the number of layers of particles that you add, then you get surface reconstructions, but you still keep the 5-fold symmetry. So that even doesn't pack in 3D space. These were some of the first electron microspectrographies that we did. This is 10 years ago. We're now much, much better, but you already still recognize, and the colors are bond order coordinated. So colored by bond order parameters. I'm not going into the details in the simulation, and we found beautiful icosahedral structures, pure ones in the core, and then surface reconstructed ones on the outside.
Just like you have on each 3D section sort of has a triangular base, right?
Yes.
What's the structure inside of each of those?
People just, because they it says more quickly that they say FCC-like. So
Okay.
but it is not FCC, because if you would have FCC stacking itself, then you would have a few degrees left in your pack. So it's saying another way, it's distorted FCC 5 points, if you want, that you see here. And these have different colors, because if this is FCC-like, then it's ABC stacked, but here is like an HCP layer in between. Otherwise, you wouldn't be able to fill them out. But it is not FCC because it's a different crystal group. It's an icosahedral symmetry.
Inside of each one.
Yeah. Yeah. And we found the same, but then you have to wait weeks in the self-assembly, and you have to turn it around to negate gravity with the 1 micron spheres, and with the PMA spheres, we recently found the same thing as well. So roughly, pure icosahedral shapes for a couple of thousand, surface reconstructed for a couple of tens of thousands. And this limit I should now shift. We thought it was 100,000 where it went to FCC. Some Japanese group a year ago published that it's actually several 100,000 where it goes to FCC. So very many experiment, no, not yet computer simulations. So Laura Fillon is now trying to see if she can also do it with several 100,000 particles, which is not so trivial. So Vinny Manoharan, together with the group that he works with, and I think also a group that Paxel works with, and we mentioned it in the paper, but unfortunately they were a little faster to do it than us. They used silica, and everything scales if you just have hard particles and you wait long enough. In this case, it's not 1 micron, but 300 nanometers is the largest. You can make structural colors. Actually, that screen look a little better, but red, green, and blue, and red, and here absorption has been added as well, because there is graphite in between to kill off the multiple scattering. But the colors are, I think, already quite amazing, and they show that indeed the icosahedral is structurally more omnidirectional than if you go to larger ones where it becomes FCC. What we recently did is we used monodispersed titanium particles with a silica outer shell, and indeed got the same supraparticles. And these are now, because the titanium is still amorphous, so it's only index of 2, but compared to silica, it's index 1.45, already significantly stronger. And this is just a cracked one. because now with confocal microscopy, we cannot look inside, of course. So this is very strongly scattering. We can do the slice and view, but just crack it open and you also see the symmetry. And this is not showing the colors very well because this is in a focused light microscope. But if you show them with an ordinary beam, they look strongly colored.
I want to understand something just a little bit better than these things. So you say it's icosahedral inside, but in looking at it, you see these triangular things with what one would normally say looks like a grain boundary between them. So what's going on? Something will be changing as you go from this one to the other, and they just differently oriented.
Yes, but now comes my point to why I hate to say that it's what is used in literature a lot is to say, oh, these are FCC grains, but they're not. They're not. So it's important. Why? Because if it would be FCC grains, then you would see much more color change.
No,
because it's all icosahedral.
No, but that's not.
The only directionality is
That's
kind
not
of building.
That's not the point I'm
Okay.
trying to get at. Rather, I'm trying to understand what each of those sections are. You say each one's icosahedral, I get it, that's fine. But there's still some kind of grain boundary between them. So what, that you can see with your eye. So what's going on as you go from one to another?
It's still spherical symmetry. So if you just solve, because they numerically solve Maxwell's equations, it does indeed show that the directionality of the color that comes up is much better than for FCC. So it's not different single crystals. That's my.
I'm not trying to put it, I'm not trying to put the peg in any particularly shaped hole. I'm just saying I see things that look like grain boundaries and I'm trying to understand what those things are that my eye sees.
Yeah, so they're not exactly grain boundaries. That's the.
So the point group symmetry cannot be. I mean, the system cannot have 5 tones, otherwise it would have to be positive, right?
No, we'll get there.
For it to be like that everywhere. I mean, to me, it also seems like they're basically path structures, which are nearly OCC, which are separated by grain boundaries. By the way, there is I think an algae in nature that does the silica particles. It looks exactly the same. There is he basically makes 5 sheets that basically come together into a 5-fold structure, and it was believed to be, when he was first observed, they couldn't actually tell the boundaries apart, and they thought that they found.
Yeah, so
they basically conflicted with crystallography, but
so also these are not quasicrystals, but we're going to, if you do it with 2 size spheres, they become quasicrystals. So but also these, if you look at it, don't have any of the scattering of the point group of FCC. So it's not twinned FCC, but it has a real 5-fold symmetry. Also, if you do the scattering experiment.
it does.
Yeah, it's finite clusters, so you can get 5-fold.
Is it like a prime Pascal or something like that?
Yeah, it's if you want, it's not a crystal because, well, you can actually just keep stacking them for forever, but there's several thousand or 10,000 particles or 100,000 even with icosahedral symmetry.
So I guess the question is, what's the unit cell of that thing?
The unit cell is the particle itself.
The entire.
Yeah, yeah. So that's why it's not infinite, because it will only go to a few 100,000 particles. But for all optical practical purposes, a few 100,000 particles is the same as an infinite unit cell. But yeah, that's indeed a good point. I'll try to quickly first go over what happens if you make them not spherical but round, and then first sharp round. Then happens what you would probably expect from packing arguments. Cubes, you try to pack as closely. Actually, they don't like to be in a sphere, but they become in the center. They become simple cubic. If the crystals like the iron oxides also in the cubic family, that's not very interesting. But if you make rounded cubes like this, you can also do that. So we define a shape parameter, which tells you if it's 0, it's a sphere. If it's 1, it's sharp cube, and if it's in between, it's a rounded cube. So boring if and already I want to point out that these simulations were done with hard shapes, but we had to take the ligand, which is only 1.5 nanometer on the core, into account to correctly get the same order of magnitude of particles that do the onion shell formation and still following the surface tension. So if we did the simulation with the shape parameter of 1, it would have already looked significantly different from the experiments. But the more interesting case, and that's what we were after, is if we make them more rounded, so that you don't get simple cubic inside, but you actually get back to this icosahedral structure, because they start to be rounded enough, but their neighbors feel still that there is a flat face on them. So that because these are single crystal iron oxide particles, they then can do directed attachment, because their local neighbors are in the same orientation, but their overall is then icosahedral and not simple cubic anymore. So then you make interesting semiconductors with topological interesting properties. Oh, you also, Paul Jakin would have loved this. You get the defects that you expect on the surface, but I won't go into that. I also, if there are questions later, I can answer that. And Michiel Hermes did a terrific job. These are almost round nanoparticles, and yet he was able, by the simulation, and not by the simulation, by image processing, using bond order parameters on the outer rim to get the orientations. And so that I can say that that's not a trivial thing. So we got all the positions and the orientations of these almost rounded cubes. You can find in the HTML files, you can play this in your own browser if you want. So this particle is going around. This is only the outside surface. And this is the midplane that is then changing. You can see that the local ones have the same colors around them, but you also recognize the fivefold symmetry. So the overall is icosahedral symmetry, but locally, if you burn away, we did it, burn away the ligands, you can form a 3D directed single crystal of the iron oxide with holes with the shape of icosahedral symmetry. And this is the simulation. Looks a little neater than the experiment, but very, very close. And we looked at the order parameters of the orientation of the. This already looks like to drop down quite fast. It's true, but that's because the icosahedral order is not compatible with cube-like symmetry. So it's not yet as beautiful as these coccolithophores. These are, all these shields are single crystals of calcium carbonate. So it's not yet there, but slowly we're starting to have some control over 3D directed attachment. And something is a very good group doing also self-assembly of supraparticles that just came out a few months ago. If you use metal organic frameworks, you can make polygonic particles that are several hundred nanometers to several micrometers in size. And you can do indeed the whole same tricks. So look at scale bars now. This is a few hundred nanometers, so optically interesting. You can also make sharp cubes. By the way, for those of you who don't know the metal organic frameworks, there is a regular pore structure inside these on the order of nanometers. And it's similar like zeolites. So then you self-assemble these with microfluidics. You get very monodispersed superparticles, and they look gorgeous. They didn't do yet slice and view, but you can recognize that the cubic ones look very similar as the 10 nanometer size cubes that we use. Okay, now I want to go over what happens if we add 2 sizes of colloids and then look, and we chose on purpose one that is very famous here, so I will not go too long over the structure. already a long time ago, I found out by accident actually that these bimetallic with a size ratio of almost 1 structures, and we in Utrecht always make them hard, but the metallics of course are not hard. But these are indeed lava phases that very closely in their phase space also have quasicrystals. But what I found very interesting is that one of these lava phases, so they form in this volume fraction range for hard spheres and these size ratios. But this is a kind of different way of looking at them, I think, than they find us. But I always focus on the big dumbbells. If you do that, you actually see a big correspondence between single particle FCC, HCP, and random stacking, and these lava phases. So this is actually the one that I wanted, but we never got to self-assembly until we went to spheres, because the free energy is slightly different. For hard spheres, FCC is 10 to the minus 3 per particle, the more stable. But HCP is very nearby. The same difference is actually, so if you look at these dumbbells, they're not dumbbells by the way, but I just look at them as dumbbells. Then it's ABC stacking, ABC stacking, and the AB stacking, which is equivalent to AB stacking for hard spheres, single spheres. This is the equivalent of HCP, let's say. And then a complex stacking is magnesium nickel 2. Well, this is not random stacking, but more complicated stacking. Unfortunately, this one is the stable one, and this is not optically interesting. This one is very interesting because the large spheres, if you burn away the small spheres or dissolve the small spheres, you have 2 diamond letters. If you do the reverse, you can get the pyrochlore letters. But this one is the more stable one. So nanoparticles form this and not that. So I thought, because of this FCC-like structuring in the supraparticles, perhaps we get the magnesium copper 2-like structuring in the for the spheres. So we really had to collaborate for this with Chris Murray, because some of you in the front may even see here the single lattice planes of the nanoparticles. So this is ridiculously small cores. So it's almost plus or minus 1 lattice plane that the polydispersity is. Why? Because the size ratio is 0.8, and you don't want them to have overlapping size ratios. So very small nanoparticles with the ligands included, monodisperse enough. So 1% and 2% is incredible for such small particles. 1% polydispersity. It literally is, I think, 1.5 lattice plane. And then, if you look, this is what Chris Murray and others in the field show it to be magnesium zinc 2. But this is cheating. If you have a random stacked crystal and you look in a certain directionality, it looks crystalline. So in certain zone axis, you don't see the random stacking. And that's what all the nanoparticle people do, because they don't like what they see in the other directions, because it looks like a mess. And because it's very difficult to do electron microscopy tomography on not supraparticles. So that's how they concluded it's magnesium zinc 2. As a matter of fact, it's randomly stacked often in their case as well, but never shown. So I have I borrowed this slide from Sarah Ball's. If you only look at projections, you think you see some of that top star over there, but that might be the wrong conclusion. So this is the projection of that guy over there. Another dead pop star. So for very many experiments, Da Wang didn't get any result of the spherical confinement on the supraparticles. We found these randomly stacked crystals until at Christmas, when he was not supposed to do any experiments anymore because he had to write his thesis. He changed the stoichiometry with very, very small amounts, and all of a sudden popped up the 5-fold symmetries that we've seen before. And then we saw a very big influence of the spherical confinement. So what was the case? we now are fairly sure that if you are slightly off stoichiometry, then you have an excess of big spheres or small spheres, and they stay like a liquid and therefore mediate the effect of the spherical confinement. So then you actually get a crystal as if it's bulk crystallization. Only if the crystal is exactly correct for stoichiometry, then the crystal reforms into this 5-fold symmetric, and indeed it turns out to be icosahedral binary crystal in 3D. And if you then take in the right zone direction of 5-fold symmetry the scattering, and this is only 6,000 particles, so it's by far not ideal, but you do find the 10-fold symmetry, and it's actually extremely similar, although this is still slightly better, but not an all of a lot better than the icosahedral 3D crystals that Schechman got, and that were 3 months later also explained theoretically by somebody who I see here a lot, Doug Levine and Steinhardt. So also, and this shows really that this is an icosahedral structure. If you go over this line, you should find the golden mean appear back. So the golden mean is shown here. It's called the tau sequence. And although we only have here 6,000 particles, it comes back to actually almost the same accuracy as the first data obtained by Schechman. So now, so a very subtle question that's not yet answered is this? Oh yeah, and first I'll show you what we often saw. We saw beautiful single crystals, but all like bulk crystals, so not icosahedral at all. But that's because of this slightly off stoichiometry of the small particles. By the way, this is very handy as well, because if you go off stoichiometry, you can study in these systems bulk crystallization and nucleation as well, because you don't always want things to be influenced by the spherical wall, of course. So, but if you are on the right stoichiometry, no excess particles, then you find the 5-fold symmetry with all the different sizes that we saw. And I show here these 5-fold symmetry directions. They're actually fairly hard to find. You have to turn all around in the right direction. And associated with this 5-fold symmetry are, for people who know about these quasicrystals, are Bergman clusters, and they are found. Why I think that these are different from the single component ones is that these icosahedral quasicrystals don't have the symmetry of the sphere. And the Bergman cluster is at a different place all the time, both in the simulations and in the experiments. So I think this is a cookie cutter 3D quasicrystal where the frustration makes the free energy of the quasicrystalline the lowest free energy. So this is different than the spherical icosahedral structures, which are their own single crystal. So this is, I think, a part of a 3D quasicrystal. And because of some defect or not defect, but an error in the simulation, we had only big spheres on the outside, but Tunista with the 3,000, 6,000 particles could even look on how they grow. And they grow by nucleation and growth. I didn't mention it, and I took it out of the talk, but the single particles grew very differently. They grew by crystallizing at the wall, then the crystals grew in, and then the wall part of the crystal recrystallized. Here, they grew. I have a few snapshots because the movie is much too big. This is the Bergman cluster, which has the 5-fold symmetry going around it, and that always nucleated the crystal, and then the crystal kept on growing until it filled the whole part.
So how sensitive is it? How sensitive is it to this stoichiometry simulation? So if you fix the volume, how much?
This took so many weeks that we have not yet gone off stoichiometry, but we will. Because there is now a new PhD student started, and there is much more efficient code, event-driven molecular dynamics by Frank Smallenberg. He spread up the code by a factor of 100, And now we can deal with that. Also in a better way, because these are hard walls in the simulations, but that is not what is happening in the experiment. There is surface tension there, and that we can bring in the simulation now as well. So we didn't want to do it because it would not be representing the experiment anyway. And now we can do that, we will do it. But the answer is not yet there.
So if you were to summarize like minimal ingredients to make this work, you're gonna do size ratios, so it'd be volume
Yeah.
fraction of one.
That doesn't matter because as long as so you can start with a very low volume fraction, but then you end up with a very small superparticle. But so volume fraction not important, but size ratio.
Oh, it's ultimately the volume fraction matters. They don't form until your droplet gets smaller enough.
Sure. Yeah, but then you get very small superparticles. But yeah, okay.
So volume fraction does matter.
It matters, but not for the kind of structure you get.
But then let's say you fix the volume fraction.
Yeah.
You say
And if you then make all the droplets all the same, you get the same superparticles. If you have the stoichiometry right.
And the stoichiometry is basically how many red particles per blue.
Yeah, and this here it's simple 1 to 2.
1 to 2. Okay,
Yeah.
so
And you need to be in a certain size range.
So specifically, in your case, it's 1 to 2 ratio of red to blue. It's what,
Yeah.
0.8, it's like
Size ratio.
80%.
No, the
Radius.
0.8 is the radius, yeah.
compared to the
But you
other.
have to take along the surfactant as well with that. And with nanoparticles, getting the stoichiometry exactly right is not trivial. For bigger colloids, it's easy.
Why can't you just titrate into particles? One?
Yeah, but the actual determination of exactly the volume fractions from nanoparticles is not trivial.
And they have to be nanoparticles?
No, that's just what we did. So
Okay.
now we're working, that's this slide
Okay,
of
sorry.
particles of several hundred nanometers, because we want to do this in the optical.
Well, just one more question here. So these are equilibrium structures.
Yeah.
All right. But then there's the same question about finite size. You know out to how big of a radius these are the equilibrium structures?
No, because the other ones we were wrong as well. We thought 100,000. Here we know for sure that several 10,000, because we can still then get electrons through to see from the outside that it's a quasicrystal. But through bigger ones, we couldn't get through, so we don't know. We could do it if we would slice them.
And the simulations haven't gotten to.
No,
part
the
of it.
simulations haven't gone bigger than 6,000.
Yeah.
But
But
now
you
with this
did-
100-time increase, we hope.
But I guess you would expect the same thing, sort of eventually.
Optimally or optimistically, I said I expect 100,000. Yeah.
Yeah.
But then perhaps it's even a few 100,000 because I was wrong with the 100,000 as well. But, yeah. So now we have. I'm going, I think, over time. So apologies. With 3D stimulated emission depletion and very small and very non-dispersed for shell particles, we can get the coordinates now, and now we want to do it with optically sized particles. In this, I will now go very fast because I'm already way over time. What we're also now doing, these are the first steps to make these superparticles dispersion superparticles, so that the particles are not dried up and not doing anything anymore, but that they can still literally move. So we can make also, notice here that this is rough and that is smooth, but we can make all kinds of coarse shell particles. We put that in a liquid cell electron microscope, and then we can, with nanometer resolution, look at what do these particles do, for instance, in these kind of shells. And then we have an electric field and we move that to different frequencies. Well, then very complicated things happen. With CONSOL, this is now accepted in the Journal of Colloidal Interface Science. We roughly understand what happens. So in this case, they move along with the field, but with these frequencies, they actually move more perpendicular to the field. It's a delay of the double layer with respect to the conductivity of the shell and so the whole story. And here, doesn't move anymore, but it's also supposed to higher frequencies become random again. So if you make this in a crystal, you can drastically switch what the Bragg peak will do, because all the particles also go in phase. By the way, if you do this, this is already showing that if you put rods in a sphere, in a field, you can make them all go to the outside, or with different frequencies, you can get them all to go into the middle. So this is with rods of 1 micron, but we've now done it with rods of 70 nanometers length as well. So you can make neat particles that are either index matched, then you switch your field on, and then they become big scatterers because all the refractive index is now at the edge. So this doesn't only change the scattering properties drastically, which by the way, very cute, try to do some holography, I think, but also changes, well, and then very fast we can make these silica rods also with ellipsoids of hematite in with all the same direction. We can put nanoparticles in their head. Then they self-assemble in beautiful ways. This is actually smectics where 80% of the heads are together. We think it's from the vase. But with magnetic field, you can make rollers out of them. And that was work of Driscoll, who worked here on the rollers with Paul Jakin. But they also, and we're very interested in that, form 3D active particles. So you can also have these particles move in the shell as well. This is electron microscopy tomography, where the E-beam dislodges the particles and they start diffusing around in the shell. But these are now reflection images of these same particles. So the hematite with the rod, the hematite scatters much more. So you see some very faint little twigs sticking out. That are the rods. Now we add some fuel and then they shoot up in 3D. So these don't move over the surface, but they go in 3D. Now comes the fuel, I think. It's perhaps hard to follow individuals, so I asked PhD students, can you make a time-framed loop system? So when they're colloidal, it looks like this, but then when the fuel is added, you can see the path of the colloids, and then you very clearly see these paths are actively and moving very fast in 3D. Okay, finally, the conclusions. Spherical confinement is very interesting, fundamentally, but also so interesting for photonic application. That we're working on right now. This is already the published stuff for nanoparticles. And I think I hope to have given you a few inkling that there is indeed a lot that can be done at multiple length scales as well. And that these dispersion supraparticles, so particles that you don't fully drive, but put a silica shell around so that it can become dynamic, are very interesting for future tunable applications. And with that, I want to thank you for your attention and apologies for too long talk.
Maybe we'll take a few questions. David, so way back when you introduced the whispering gallery modes and talked about the laser, the laser lines looked like they were at sort of 1 to 2 electron volts. Is that right? I mean, are they very, very, very blue?
Yeah, these were huge superparticles, so 10 microns. And you saw even two modes sometimes, so not only one mode selected, but two. If the packing can be increased, which we're doing right now, you can bring them to be lasing already when they are 5 micron as well.
And they're lasing in the UV, is that right?
No. They were lasing in the blue part, but still divisible. Okay. There was a second. I don't. You like the electron volts. I don't. So I always put an.
I don't like electron volts. I had to look it up.
Okay. Yeah. The same here. So I always put double axis there. Oh, which wasn't done here. So I apologize. So I always ask for the stupid me because I can't do 1 over things. So actually, these are not blue; they're red. Yeah. So this is the same, but it's not that. But here you can. I would just only look at the top one. So they were not blue, they were red, sir.
Chemists here want to know how many kilocalories.
No, that's old chemists. The modern ones want kilojoules.
Oh, but there's also calories that the kilocalories, that's.
Well, cow with a big C,
With
you
a
know,
big
same as
C.
kilocalories is mostly.
Exactly, you know about that. Great.
So, are there other questions?
Let's say,
Down in the back.
so you still did the supraparticles for the lavas, you only saw the magnesium zinc structure, not magnesium.
No. We know. And now we have to be very careful. We saw just like the FCC wasn't FCC, but FCC light. We saw actually the magnesium copper 2 light. So the analogy actually, after a year about it, worked. But it's not magnesium copper 2, but it's really, so magnesium copper 2, even if you would put it together like that in a sphere, would not have a tau sequence. So it's slightly deformed magnesium copper 2. But slightly means already a few degrees. So optically, that's enormous. That means different space group. But to think about it, it's still those 5-fold symmetry things were indeed magnesium copper 2. Like. Yeah.
I have a question about comparing drawing droplets versus like on a surface, which I've seen other people work on.
Yeah.
So there I've seen things with like pattern formation, and also we've seen things like coffee ring effects, things like that. Is the reason you have more equilibrium structures because it's symmetric, or what's
Now, well, two things. All these copper ring and so on, I'm familiar with. But the reason we do it slow. But if you would do it with nanoparticles, it can be as fast, because a postdoc of Chris Murray has just published a paper where he still got the icosahedral structures in 2 minutes. So that's that R to the third. If you go to particle diameter of 8 nanometers, then equilibrium, because they have to do a lot of recrystallization to actually form these icosahedral ones. So it's true. But if you do it for 300 nanometer particles, you need to be 8 hours. But if you do it less, you get what they call onion shells, so only hexagonal rings and then amorphous. If you do not even faster, you get amorphous totally. If you do it even faster, you get a shell only. But if you do it very slowly, you get the icosahedral, well, very slowly, 8 hours. But this scales with this R to the third.
so in a sense it is similar, it's just that you can get all the way to.
Yeah, so we just have a very tiny hole and evaporate very slowly.
Yeah, so I have two questions. So one question is, so you've shown different particle shapes, and I was wondering why, I don't know if you tried the shot, or you guys tried
Plates.
tetrahedral,
No,
because they make
yeah, beautiful.
structures.
Yeah.
Naturally,
that would be
right?
very
They
interesting.
pack perfectly.
Yeah.
If it is true that they are icosahedral throughout, right? Then they should pack in a massive icosahedral.
Yeah, they would even do it or keep doing it. Actually.
Yeah, exactly.
So these stop at some point.
Yeah.
Yeah, no, we haven't tried that. So you can make also the nanoparticles with an icosahedral shape, or with a rounded tetrahedral shape. Yeah.
And the other question is whether.
By the way, they're two famous papers. I think one Nature and one Science or so of these, but they analyzed only 6 layers of the quasicrystals. So we got questions about, we analyzed 30 layers. So this is by far the most in real space by any quasicrystal. And those papers only analyzed 6 layers the most, because it's just geometry. If you want to do tomography and you have a flat crystal, if you tilt it, it doesn't go through anymore. So actually, the spherical is for tomography, it's optimal.
So the other question I had was about whether this can be done with surfactant particles, so with salt particles, because there's a big question in the surfactant community about whether you can make icosahedral quasicrystals, because they get into the pattern of about 2D. and they don't know whether they can get 3D quasicrystals. So it could be interesting to see whether, you nucleate at least, right, with the added constraint of the
Likely, because
spherical.
the spherical frustration
Yeah, but they,
brings you
yeah,
towards.
but they exchange.
Yeah.
Chains, right? So
Yeah.
they're shape chain.
Do they always exchange chains? They don't have to. Some do, some don't.
I thought they always did.
Yeah, I've looked them up because I want to find out, have they found an icosahedral 3D cross crystal? I don't think, I've not found it.
All the
Have you found one?
I'm thinking
all
of
the
like
surfactants in dinos form two D quasicrystals.
Yes, there's plenty. We show many times. But 3D icosahedral quasicrystal, it's like,
Yeah,
I've not found it. If you
A
find the
holy
reference, I would bring a slide to you.
or what?
Of these microemulsion, I call them microemulsion systems, but
Yeah.
but squishy
Yeah.
soft matter systems. I looked for them, but I couldn't find the 3D processes.
No, they,
No,
they're
no, there
not
are-
been able to find it.
No,
They're-
I think his question is, there's several 2D.
Yeah, and
ones.
if you put
And the
those in
question is,
sphere,
they put those in a
yeah,
sphere
no,
because
it has not been done, and very interesting.
No, and what I was saying, I was telling you that I know several people that are working on trying to get the icosahedral or the crystal with the system in 3D, and they've not been able.
If you don't mind telling them who these groups are, I would love to,
Yeah,
to
okay.
collaborate. No,
But
but the analysis in 3D is much harder because we do. I leave all the details away, but the ligands, if you do tomography, the ligands are not very happy with all these electrons. So we first have to very slowly get rid of the ligands. It's called beam showering by electrons, and then the structure is stable enough to be able to do all this. But these will be, well, actually, so with scattering it's certain.
Yeah, these guys.
But, yeah, okay. In real space, very good.
Okay, listen, we've gone on quite some time, so I'll let's thank Alfons once again. So,